Hello everyone. In this video, we will learn to state the postulates of kinetic molecular theory of gases and use the kinetic molecular theory to explain various gas laws that we discussed so far in this chapter. So far, in this chapter, we learned various gas laws that explain the behavior of an ideal gas. For example, Boyle's law states that the pressure of a gas is inversely proportional to its volume. Charles' law states that the volume of a gas is directly proportional to its temperature. And Avogadro's law states that the volume of a gas is directly proportional to the number of moles of the gas. First, let us try to understand what a law means. A law is empirical in nature. That is, a law is based on experimental observations. For example, if you increase the pressure of a gas, its volume decreases. Based on this observation, Robert Boyle proposed his law called as Boyle's law. Even though a law is always true and that it summarizes the observed behavior of a gas, it does not tell us why a particular behavior is observed. For example, the Boyle's law does not explain why the pressure of a gas is always inversely proportional to its volume. To explain these experimental observations or laws, scientists build models or come up with theories. The theory that we use to explain all these gas laws is called kinetic molecular theory of gases. There are 5 postulates in kinetic molecular theory. Postulate number 1. A sample of gas consists of a large number of gas particles, and these gas particles are constantly moving in straight line paths and in random directions. When the gas particles move, the particles collide with one another and the walls of the container in which the gas is placed. When a particle collides with another particle or the walls of the container, it changes its direction. This random motion of gas particles inside a container can be compared to moving balls on a billiards table. That is, the balls collide with each other and with the edges of the pool table. Postulate 2. The pressure of a gas is because of the collisions of gas particles on the walls of the container. When a gas particle hits the walls of the container, it exerts some force on the walls. This is similar to the force exerted by a macroscopic object. For example, a billiards ball collides with another ball, and during the collision, it exerts some force on this new ball. The collective force of all the gas particles on the walls of the container is nothing but the pressure of the gas. Postulate 3. The distance between the gas particles is so large when compared to the size of the gas particles. Therefore, the real volume of the gas particles can be assumed as negligible or close to zero. This is the reason why gases can be compressed to tiny volumes. In contrast, solids or liquids have no empty space between the particles. Therefore, they are not as compressible as gases. Postulate 4. The gas particles neither attract nor repel each other. That is, during the collisions, there are no attractive or repulsive forces between the gas particles. In reality, the gas particles may have dispersion forces or dipole-dipole forces if the gas molecule is polar. However, we assume that these forces are negligible and that when a gas particle collides with another gas particle or the walls of the container, it results in an elastic collision. That is, there is no net loss in kinetic energy when the particles collide. Postulate 5. The average kinetic energy of a gas is directly proportional to the Kelvin temperature of the gas sample. That is, if we increase the temperature of the gas, the average kinetic energy of the gas particles increase. We know that the kinetic energy Ke is equal to half mv squared, where m is the mass of the gas particle and v is the velocity of the gas particle. The mass of the gas particles does not change with the temperature. Therefore, the increase in the kinetic energy is solely because of the increase in the velocity of the gas particles. In summary, we can say that the gas particles move faster as the temperature increases. These postulates of kinetic molecular theory of gases look so obvious. However, they are very powerful in explaining the behavior of a gas. Let us now learn how the postulates of kinetic molecular theory explains various gas laws. According to the Boyle's law, pressure of a gas is inversely proportional to its volume when temperature and number of moles of the gas are kept constant. Let us now understand how kinetic molecular theory explains this relationship. According to kinetic molecular theory, the velocity of the gas particles depends on the temperature of the gas. Therefore, at constant temperature, the particles have constant velocity. Now, at constant velocity, if we increase the volume of the container, the particles take more time to travel and hit the walls of the container. Therefore, the number of collisions on the walls of the container decreases. And as a result, the pressure of the gas decreases. In contrast, if we decrease the volume of the gas container, it takes less time for the gas particles to hit the walls of the container. That is, the collision frequency or the number of collisions per second increases and the pressure of the gas increases. This is how the kinetic molecular theory of gases explains the Boyle's law. That is, the pressure of the gas is inversely proportional to its volume. Next, let us learn how the kinetic molecular theory of gases explains the Charles law. According to the Charles law, the volume of a gas is directly proportional to its Kelvin temperature at constant P and number of moles. When we increase the temperature of the gas at a constant pressure and number of moles, the velocity of the gas particles increases, which increases the frequency of collisions, and therefore the pressure inside the container increases. To keep the pressure of the gas constant, the volume of the gas must increase. Therefore, at constant pressure and number of moles, if we increase the temperature of the gas, the volume of the gas increases. In the same way, we can explain the other gas laws such as Gay-Lussac's law and Avogadro's law using the postulates of kinetic molecular theory of gases. In addition, we can also derive the ideal gas equation using the postulates of KMT. However, the derivation is beyond the scope of this course.